Okay, so good morning, everybody. I'm José Javier Imas, a researcher from the Sensors Group here in the Public University of Navarra, and I'm going to present some of our preliminary results about lossy mode resonances and NRs in polymer-based photonic integrated circuits on behalf of all the authors that include Dairon Armas and Professors Carlos Ruiz and Nacho Matias. Well, it's not easy now to talk about lossy mode resonances after Professor Del Villar, but I will try to do my best. Okay, so I will give an introduction. I'm going to repeat a lot of things that were said before, and I will then focus on the lossy mode resonance design. I also will talk a bit about the grating coupler, and then I will finish with some conclusions and future lines. Okay. So this is a cladding removed multimode fiber where in the region where the cladding has been removed, a thin film has been deposited. And if we transmit light through the fiber, the Manstein field of light can interact with the thin film material and different type of resonances can appear. We could monitor the resonance at a single wavelength and see the changes in intensity, but we usually monitor the full spectrum as power versus wavelength. So, of course, we need a broadband light source as excitation, and we usually use as the data acquisition system a spectrometer or an optical spectrum analyzer, which is usually connected to a computer. So these are like the classical conditions that we always say for generating lossy mode resonances, LNRs, or perhaps you are more familiar with surface plasmon resonance, SPRs. You see like the conditions are pretty much the same. The critical difference is that here the real part of the permittivity of the thin film material has to be positive, and here it is negative. It's instead of these conditions, it's easier to say that if we are with the electric materials whose real part of the refractive index is much higher than the imaginary part, let's say metal oxides and polymers, we are going to generate lossy mode resonances. If we are with materials where the imaginary part of the refractive index is higher than the real part, which are metals such as gold or silver, we are going to generate surface plasmon resonances. It's easier to think in terms of materials instead of terms of these equations. We have another way to define the lossy mode resonances is to say that it's the resonance that appears when there's a phase matching between the fiber core mode and a lossy mode in the thin film. Okay, so how do we end up talking about integrated photonics? Because here we are mostly more familiar with fiber. Okay, so the first LNRs were done in cladding removed multimode fiber, as I have shown in the previous slide, and we have usually aimed towards obtaining high Bull sensitivities to the surrounding medium refractive index. And if you want to achieve a high sensitivity, you have to work at the longer wavelength possible, but the problem is that if you work at longer wavelengths, the resonance is going to become wider, and in the end, it's not practical to do a sensor with a wide resonance. So in order to try to solve that, we started working with another structures, as Professor Del Villar said, single mode structures, as the taper single mode fiber and the D-shaped single mode fiber. They have pretty much the same sensitivity, but the resonance are narrower, which means that we can go farther into longer wavelengths and still have resonances that can be used for sensing applications. So in the end, as we can work at longer wavelengths, we achieve higher sensitivities. What's the problem with these structures? Well, that they are fragile and they tend to break very easily. The first week of my PhD thesis, I don't remember how many of those I broke. So another platform that was explored in order to see other possibilities were planar waveguides. Planar waveguides are more robust, simple, and cost-effective than this kind of fibers, but again, it's like we return to the starting point. The resonances are again wide, so we cannot go too far into long wavelengths, and the sensitivity is we can achieve is smaller. So after studying all these platforms, well, we decided that it was also interesting to start exploring, for example, integrated photonics, which has as advantages the miniaturization, the scalability, the low power consumption, and the compatibility with electronic devices. Well, so what has been done in integrated photonics about LNRs? Well, this is a work from Letko Bundulis and other researchers from the University of Latvia, which is the first experimental time that LNRs were obtained in polymeric waveguides in integrated photonics. So they use a glass substrate, then they manufacture the polymeric waveguides. They have used different kinds of polymers, here Ormo-Clear, Ormo-Core, and SU8. SU8 is one of the most common polymers used in integrated photonics. And then, after that, they perform a deposition of indium tin oxide, ITO, to generate the LNR, which you can see here. These are Lossy mode resonances of different orders. So this work is really interesting because, as I have said, it's the first experimental result of this kind. The problem or the main drawback is that the waveguides are really large. They are 100 microns per 100 microns, which for integrated photonics, where dimensions are usually in the order of a few microns or less, it's too large. This means that then if we want to combine these LNRs with other devices within the same chip to get a more complex structure, it's not going to perform well. So in order to find an alternative, we started to study this problem between researchers from here and also researchers from the photonics and RF group from the University of Malaga, whose leader is Professor Íñigo Molina, who was here yesterday. And we wanted to study a standard platform in integrating photonics, and silicon on insulator is the most used platform in integrated photonics right now. So silicon on insulator, you have a Hondel layer made of silicon, then you have a barium oxide of a few microns made of silicon dioxide, and then you have the device layer, which is usually silicon, but you can also use, as here, silicon nitride. And then you have the upper cladding, which can be again silicon dioxide, or it can be air. Here it's air. So here we propose this design. Here we have a silicon nitride photonic wire, which is 2 per 0.3 microns, and then there is a doped silicon layer on part of the photonic wire. This silicon, it has to be, well, it has a higher refractive index, so it can generate a Lossy mode resonance, and it has to be doped in order to have some level of losses to generate the Lossy mode resonance. And the theoretical result we get is this one, that is much narrower than this result, and in fact we are also working in the infrared, which is more interesting. What's the problem of this? That even if the resonance seems better, the problem is that this is difficult to manufacture. The silicon nitride photonic wire is pretty standard, but the problem is how you do this. You need to perform the deposition of a silicon thin film only on part of the photonic wire, and what's more, it has to be doped, which is, if you ask for this, it has to be like very ad hoc, and it starts to be like really expensive. So this it gives good results, but it's not a practical implementation to do this. So now we are starting to explore, again, trying to explore using polymeric waveguides. So this could be like a silicon plus silicon dioxide wafer. Then we have to manufacture the polymeric waveguide. We are trying to use EpoCore. EpoCore is a polymer which has pretty much the same refractive index as SU8. And then we would generate the Lossy mode resonance using titanium dioxide, which also has losses. So when I have started to try to design this, and the problem I face, or the challenge I face, is that when we are usually thinking in terms of the optical fiber, the only degree of freedom for generating the LNR is the thin film thickness. This happens because, as I have said, you need a phase matching between the fiber core mode and the lossy modes in the thin film. So, if you change the thin film thickness, the fiber core mode isn't affected much. So if you are changing the thin film thickness, you are only changing the lossy modes, so it's easy to achieve a phase matching with the fiber core mode. Here the problem is that if I start performing simulations and I change the thickness, the lossy modes in the thin film change, and the modes in the photonic wire change too. So it's not as easy, it becomes trickier to achieve a phase matching. And there are also other degrees of freedom. Here we have the height and the width of the photonic wire. In integrated photonics, usually the height of the waveguides is fixed by the commercial foundry where you manufacture them. Here we are trying to do that ourselves, so it's another degree of freedom. And the width is usually selected to have single mode waveguides. But here I have been simulating, and I'm not so sure that single mode waveguides are the best solution for doing this. So, as I have said, this is tricky, at least for me, and I have 3 degrees of freedom, and I didn't arrive to any magical procedure to get a good design, so I decided to do a triple parameter sweep until achieving a sweet spot. Okay, so I arrived to this design. I arrived to a width of 2.5 microns, a height of 1.2 microns, and a thin film thickness of 230 nanometers. I have lost my chronometer. Okay, so this is for generating a T-polarized LNR, because as Professor Del Villar has said, the LNRs can be T-polarized, or TM transverse electric polarized, or TM transverse magnetic polarized. Okay, but what I can explain is this gives this spectrum, taking into account that this is only 100 nanometers, and I can explain why this gives what I would say this is a good result, a good lossy mode resonance. This graph, it corresponds to the modal analysis of the second section, the section with the thin film. And here the effective index versus the wavelength. And here I have remarked 3 modes, one in red, one in blue, and one in green. And here, if I have done a close-up, there is a phase matching between the mode I have called mode A and the mode I have called mode B. And I also remarked this one. This could be what's called the fundamental mode, which is the one that has the highest effective index in the section. And I'm also going to add to this graph the effective index of the T0 mode, which is the mode that is excited in the input section, in the one without thin film, to generate the LNR. This graph shows the power transmission between the T0 in the transition between the section without thin film and the section with thin film, the power transmitted by this T0 mode in the first section to all the modes in the second section. And we can see that most of the power is transferred to either mode A or mode B, and there's also a fraction of the power that is transferred to the fundamental mode of the second section. This is easy to explain if we see the modal fields of the modes of the different wavelengths. So below the anti-crossing, the mode that has the more similar mode field to the input mode is mode B, more than mode A. This is close, let's say, to the mode that is excited. So most of the power is transferred to mode B. At higher wavelengths than the central wavelength of the anti-crossing, mode A is more similar to the T0 mode, so most of the power is transferred to mode A. And at the central wavelength of the anti-crossing, which is around this point, we see that the modal field of both modes is similar, so more or less half of the power goes to mode A and half to mode B. If I now also plot the imaginary part of the effective indices, which is related to the losses of the modes, with this graph, these two graphs, I can explain this output power spectrum. Below the anti-crossing, this mode receives most of the power and it has low losses, a low imaginary part. After the anti-crossing, mode A receives most of the power and it has low losses. And only during the anti-crossing, both modes receive an important percentage of the power from the input mode and have relevant losses, which explains the peak we see here, which is the resonance, which is what we call the lossy mode resonance. So the central wavelength of the resonance matches the central wavelength of the anti-crossing. I have not mentioned this mode. This mode receives power and it has high losses. So if the second section is long enough, all the power that this mode receives is lost along the section and we don't see it in the output. If the second section was short enough, this mode would arrive to the output of the device with power, and here we would see interferometry in all the spectrum. So, apart from these parameters, other parameter I have just mentioned is the length of the device. So, in the previous results, the length was 250 microns, and here I have done a sweep of the length. So we see that if we take a shorter length, the lossy mode resonance is not pretty much visible. If we increase the length, the resonance becomes narrower, which is interesting, but we also have more losses, which is not interesting for a practical implementation. So, well, maybe 400 microns could be or not, depending on the power we have and the detector we have, than 250 microns. Obviously, further increasing the length is not positive because the spectrums start to worsen and start to have a bad shape. I have also studied, well, let's simulate the sensitivity to the surrounding medium refractive index. All these previous results were in air, so I had simulated the shift, what happens if we change to water, and then changing the refractive index in aqueous media. So the sensitivity between air and water is around 500 nanometers per refractive index unit, and the sensitivity in aqueous media is 900 nanometers per refractive index unit, which is not very high, but it's not bad because in integrated photonics, sensitivity of around 1000 nanometers per refractive index unit is a good number. Okay, so after designing this, what I also need is how to couple the light in and out of the chip. So there are different options. There are edge couplers, grating couplers, and other different options, and I have decided to design a uniform grating coupler. So the design parameters of the grating coupler are the grating pitch and the duty cycle. So the procedure to design this one I know as the other one, is you perform a sweep on both the pitch and the duty cycle, and you measure the reflectivity in the input port. We are using the T0 mode as the input mode because it's the one we are then going to use to excite the lossy mode resonance. So depending on the reflectivity, we distinguish different operation regimes, which are the sub-wavelength rating regime, the Bragg regime, where light is reflected, and the radiation regime. If one wants to design a rating coupler, we need to operate in the radiation regime. So within the radiation regime, I select an area that I find interesting, and I have to perform an additional optimization step. Now I have to study both the fiber angle and the pitch and the duty cycle. So after performing a sweep here, I have arrived to this design for a fiber angle of 38 degrees, a grating pitch of 900 nanometers, and a duty cycle of 0.35. And the curve that corresponds to the rating coupler could be this one. This bandwidth is typical of a rating coupler. It's difficult to obtain grating couplers with a wider bandwidth. This means that this experiment it's not possible in reality. We would have to either design several devices with different grating couplers with different bandwidth, because we are not going to be able to cover all this bandwidth with a single grating coupler, or another option, this curve for this grating coupler corresponds to this fiber angle. If you start changing this fiber angle, the grating coupler curve starts to shift in wavelength. It also can go down, so maybe it wouldn't either be a good solution, but well, sometimes it's used. So, another thing I have not mentioned, this is a uniform grating, and I have said the width of our waveguides was going to be 2.5 microns, and usually the grating coupler has to be wider. Here I have selected 10 microns, so that means you need a taper to adapt the mode from the waveguide to the grating coupler. So I have simulated, and in order to be adiabatic enough, it would have to have a length of around 100 microns, which is long. But if you use a uniform grating coupler, you have to use a taper. So the final design would be something like this. Here you have the grating couplers, you have the section with the titanium dioxide thin film, and the section without thin film. And, well, this is what we have done right now, as the main conclusion is that it seems that we can achieve a design where we can overcome the drawbacks of previous things that have been done. Of course, the future lines is to try to manufacture this. We are already doing some tests, but we have not manufactured it right now. And in the meantime, I'm trying to obviously improve the theoretical design. One of the first things I want to do, most people would consider that is a really large footprint of the device, because it's using uniform grating couplers that need a taper. So I started trying to simulate, this is a focusing grating coupler, which doesn't need a taper, so the footprint becomes smaller and it occupies less space. So thanks for your attention, and if you have any questions, do not hesitate to ask.
Thank you, Jose. We have time for questions. Too much time, yes. Okay.
I have, well, congratulations for the good talk, very interesting. I have just one question about slide 9, where you mentioned about, the spectrum that is rather narrow, but there are biosensors that shift only 2 nanometers or 5 nanometers, biosensors with not too high sensitivity, but very narrow bandwidth. So probably I think that this design could be worth still for biosensors where there is not a big wavelength shift. That's my opinion.
Thanks for the question, Ignacio. I'm no expert in designing grating couplers, but from what I'm no expert in designing this, but from what I know for grating couplers, a typical bandwidth is from between 40 nanometers and at most maybe 80 nanometers in the case of a grating coupler. So maybe, I don't know, because I have not studied the sensitivity of these devices too much, but we usually, when we study LNRs, we are used to really large chips of more than 100 nanometers. So in that case, this doesn't seem to be the case. It's not going to be useful to use this grating coupler. This is only a simulation. From this simulation, it's obvious that if you wanted the same device to work in air and in water, the grating coupler is not going to be a good solution. Of course, from what I have seen, in integrated photonics, most designs are either done to work in air or directly to work in water. So if you, for example, did a design to work in water, you could be in this area and you could design a grating coupler to work on this area and it be enough, and you would forget about this part. But as we usually give a rough number of sensitivity between air and water, I perform this simulation. But it's probably for most applications, it's going to perform well only using a grating coupler.
Okay.
Sorry, I ask questions. What's your most sensitive parameter in this? Like, what do you really need to get right to actually your design to match your experiment? Minimum tolerance. And what would go wrong?
What could go well? Many things could go wrong. No, thanks for the question. Right now, many things could go wrong because we are already trying to manufacture things, and for example, things that are important, that the sidewalls are vertical. My main limitation now is to see, for example, if I use a grating coupler, this would be the minimum feature size, which is like I have said, the minimum feature size would be the grating multiplied by the duty cycle. So I have to know that if the systems we are going to use is going to be able to reach that minimum feature size or not. For the moment, we are still working on that. For people that are into integrated photonics, that they go to commercial foundries and know a lot about this, a rough number of the minimum feature size is 100 nanometers. They usually do the designs where the smallest dimension has to be larger than 100 nanometers. If it's smaller, they are going to have problems and they are going to have to change the design.
Any other question? In this case, let's thank the speaker again.